Hello, and welcome to this tutorial on how to make your lab data work for you using Google Sheets. Keep in mind that this video is not meant to show you how to use any particular data set, but rather how to work with data in general using these tools. Also keep in mind that Google Sheets has limitations and there are other programs available if you think that the tools available in Sheets are not sufficient for your needs. I recommend the desktop version of Logger Pro if this is the case. Now then, your physics teacher has probably helped you collect some lab data either straight into a spreadsheet like this one or into a .csv file and then asked you to make some kinds of crazy graphs and you are just entirely lost and don't know how to do that. So we're going to start out that assuming that your data is in a .csv file as if you had imported it from something like Veneer LabQuest. If this is not the case, you can go ahead and skip this step because your data will already be in the spreadsheet. So the first thing we're going to do is we're going to go to File, Import, and this is going to automatically pull up your drive. Now, if you have something like an actual desktop computer with a USB stick, you can upload it directly from there. Or if your Veneer LabQuest is plugged into your computer, you should be able to use that as well. But in my case, I'm going to pretend like it is in my drive. So we're going to go and find this .csv file. Again, this is meant to show you some general use cases. So we're going to find this data from a projectile motion laboratory. So what we're going to want to do here is insert this data into our sheet that we already have. So what we're going to do is replace data starting at selected cells. So that's going to take wherever your mouse cursor is and insert the data starting from there, going down and to the right. There we go. So now we have a whole lot of raw data. So now that we have all this raw data, it's time to work with it some. So the first thing we're going to want to do is arrange this into a more legible table. So some good first steps is just to expand your columns so that if your axes, if your data is already labeled, you can actually read the full label, including the units and all the other included information. So this is already much better, but we're also going to want to make this a little different. Personally, I prefer everything to be arranged horizontally instead of vertically, but that is a personal preference and it doesn't make a whole lot of difference for this tutorial. So the easiest way to move data around is going to be to hold down Control and Shift with your cursor starting at the top of a data set, and then hold down Control and Shift and click at the bottom of the data set, and that will select an entire set of data. Now you can also select entire boxes of data like that. But for now, we just want this one column. And we're going to go ahead and move this down and out of the way because we want our more legible stuff up at the top where everyone's going to see it. I'll go ahead and move the rest of it as well. There we go. So, this is already a lot more legible. Another thing that I would recommend is adding some borders to your data like this. This way you can separate out the titles from the actual data itself. And also if you're feeling a little fancier, you can add borders all around the edges. It's looking nice. And also you can go ahead and color in there you go. And then also, one personal preference is I like to alternate colors, so that way each table is very, very clear from one another. Like so. Now you may be thinking, how did you do that thing where you outlined a column here and a column here? So what you want to do in order to do that is you want to hold down Control and Shift and select a range of data just like I showed you before. Then let go of Shift, but keep holding down Control. Select a new starting point and then press Control down once more, Shift down once more. So now you have both Control and Shift pressed down again and click again. And now you can do this as many times as you want and select as many various data points as you would like. So now that we have a more legible table, let's make some graphs. So the first thing your physics teacher asked you to do is to do a position over time graph. So in Google Sheets in general, what you're always going to want to do is take the data that you want and just move it out to the side before you make the graph. Trust me, this is just the easiest way to make sure that nothing goes crazy. because sometimes Google Sheets will try to do some crazy things with your data and you don't want that. So now we have time and position. Again, if we wanted something like time and velocity, same trick as I showed you before, Control Shift, and just move it out of the way. So what you're going to want to do is you're going to want to select this entire data set. And then you want to go up to Insert, Chart, and this will give you some previews. Now, depending on your data, you're going to want to choose different graph types, but in general, this is probably going to be a good one to do. Just a standard line graph. And right now, the formatting is not very nice, but we're going to edit that right now. So thankfully, Google actually made some correct inferences in this case. It figured out that this should be on the x-axis and x should be on the y-axis, x being position, not the x-axis. But if it doesn't figure that out, you're going to want to move these things around right here, these checkboxes. So whenever it says use row 171 as headers, here's what that means. Here's row 171, and these are your headers. So what that's basically saying is this is what it's going to use in order to name your axes and also your line. The other thing is use column O as labels. So what that means is this is going to be set as the x-axis. Otherwise, it's going to set an arbitrary x-axis and then show two lines, but you don't want that. You want your x-axis to actually scale with the y-axis. And again, you can change the type of line that you use. In general, you're going to want to use this one, but in case you're trying to calculate something like the area of under a curve, you might want something like this. In general, this is going to be your best bet. So now we're going to customize. So you should always try to clean up your title a little bit. So we're just going to have position versus time. Make sure to include units or else your teacher will almost certainly count off points. You usually won't want to use any of these, but if you have lots and lots of data points and your data looks a little jumpy, you might enable smooth. In general, you shouldn't have to do that though. So now for our axes, we're just going to want to change this. So right now we're on the horizontal x-axis. We just want the title to be time in seconds. The rest of this shouldn't be important. And now we're going to change to the vertical axis. This is just going to be position in meters. And that is just fine. And there we have a graph. Now this is a very simple graph. You will probably be asked to make more complex graphs. So now I'm going to show you an example of a graph where you might have to have multiple sets of data corresponding with your x-axis, which is generally going to be time. Not always. Do not always assume that time will be your x-axis because you will be sad. So now we're going to make a graph that has two separate things that are both going to be varying on the y-axis. So we're going to do the same thing as before. We're going to insert a chart. And thankfully for this one, it was able to figure it out. It was fairly simple. It will not always figure it out, however. So it might do something like this. Obviously, this is not what you want. So make sure to tell it exactly what you want. Make sure to tell it that you're using headers. Make sure to tell it that your x-axis is actually an x-axis. Things of that general nature. In general, this looks pretty good. Obviously, you would want to clean up your various things. Another thing that you might want to do is insert a line of best fit. So here's what you want to do for that. So you want to find the series. Now, because we have more than one y-axis scaling variable, we're going to want to select which one we want to do. In this case, we're going to do a line of best fit for our position over time line. So this is all just, for the most part, aesthetic choices, but this is what you want down here, trend line. Now, really it's going to depend on the kind of data you have. In this case, I would say that this trend line is not linear. I would say it looks a little more exponential. But if you know the equations for the thing that you're trying to figure out, it'll be a lot easier. I actually happen to know that it is not exponential, it's actually polynomial. Now, another thing you're going to want to do is check show r squared, and that's going to show you your r squared value. Remember, a higher r squared value is better, a lower r squared value is worse in terms of how well your line of best fit matches your actual data. And you're also probably going to want to show the equation so that you can tell things like, well, in this case, it is a position over time graph, so this is going to be acceleration because it's the second derivative of x. This is the derivative of x, and this is the position, which is your velocity and your acceleration correspondingly. So I like to have a not 100%, 80% line, so you can just tell that it's not the real thing, whereas the real thing is 100% opacity. And also I like to make it a little thinner. 2 degrees. Almost any time that you do a motion graph, you're going to want to use a 2-degree polynomial because you're going to have acceleration, you're going to have velocity. If you have anything more complex than that, for example, if you're not in Physics 1, if you're doing some kind of calculus-based physics, you're probably going to want to up your degrees. As you up your degrees, your polynomial equation is going to get a lot more complicated, but it's also going to get more accurate, and your R-squared value is going to get higher. So now, we have a line of best fit. So, if you were asked to determine an experimental acceleration, you could say that using this, since the general equation is y hat, because that's your predicted y value, is equal to 0.5 at squared plus v naught t plus x initial. Now you can substitute these values. So x initial is 0.034 predicted. Your velocity, predicted velocity, is 0.157 meters a second, and your acceleration is 2.42 times 2. Alright, so the last important thing that I'm going to show you in this tutorial is how to do calculations on large data sets like this. Now, let's say that you don't know the velocity, so your VinierQuest does not actually output the velocity for you, so you need to calculate it yourself. Now, we know that the formula for velocity is the change in x over the change in time. But trying to do that for every single one of these points would be very time consuming, because there's about 40 data points right here. So instead, what we're actually going to do is we're going to use Excel's formula powers in order to automatically do all of these calculations for us. Now, this is going to require a little bit of thinking and logic, so hopefully if you're in a physics class, you've been able to work some of that out already. So, let's think about this. If velocity is equal to the change in x over the change in time, the first thing we're going to want to figure out is what the change in x is. Now, whenever you do any kind of formula in Excel, what you're going to want to do, sorry, not Excel, Google Sheets, it's the same for both. You're going to hit equals, and that's going to tell Sheets, that you're doing a function. So you're doing some kind of operation and not just entering a value. Because if I just entered 54 times 3, it's just going to type that in as text. But if I want to do the calculation 54 times 3, I have to put an equal beforehand, in which case it'll output 162. So, the first thing we want to know is what the change in x is. So this is going to be its own separate thing, so we're going to put it in parentheses because we want order of operations to work out in our favor. So, the trick here is knowing your relative and fixed positioning. So actually what we want to do is we want to look at this number minus the number that came before it. I'm just clicking on these and it's automatically inputting their positions on the graph. But remember, these are relative positioning. So what I'll show you in a second is that as you copy this formula down, it's going to remember the relative positioning. So in this case, down 1 and to the left 1, and just to the left 1. That's really what we're storing here, not actually C5 and C4. What we're actually storing is down 1, left 1, and left 1. So that's going to be our change in x because it's this x value minus the original x value, and parentheses. And then we're going to divide that by the change in time, which is going to be down 1 and left 2, which is that time, minus the initial time. And that's going to be our velocity. And now, when you hover over this, you're going to see this little box down here in the corner. So what you're going to do is you're going to want to click and drag that, and drag it all the way to the bottom. And there you have it. You just calculated all your velocities. Now this is very ugly data. You would not want this. So what you actually want to do is you want to find that, and you want to make sure that it's all a nice amount of decimal places. Significant figures are your friend. In this case, we started with, well, generally a good rule of thumb is probably no more than 3, unless you are using extremely accurate sensors. In general, about 3 is good. Acceleration is going to be the same thing. Acceleration is the change in velocity over the change in time. So we're going to do that velocity minus the initial velocity over this time minus the starting time. Copy this formula all the way down. And we're going to want to tune this down a little. There we go. And so now we also have some accelerations. Now, obviously, this data is a little bit crazy looking. So a good rule of thumb is whenever you have a very sensitive sensor, sometimes it can go a little bit awry. So a good rule of thumb is take around about 5 data points, calculate their average. So in Excel, it's going to be average. Or another good one is mean, although I don't think it actually recognizes this in Sheets. I believe in Excel you can do a mean function, but I'm pretty sure that in Google Sheets you have to do an average. So you're going to want to hold down Control and Shift, just like you're selecting any other data set. There we go. And so that's this number colon the other number, because that's specifying a range of values rather than individual values, in parentheses. Oh, I guess it's not average. Well, we'll do it the old-fashioned way. We're going to take the sum. I'm used to doing this in Excel. It's much easier. We're going to divide by the number of values, which is 5. And now what you can actually do is you can copy, right? Count down 1, 2, 3, 4, 5. And now paste special and only paste the formula. And like I said, because you're using relative positioning, it's going to look up to and down to and to the left one and set that as the range. Now, let's say that you have some constant. Let's say you have the constant, 9.81. That's the acceleration due to gravity at Earth's surface, in case you were wondering. Now, you're fairly lazy, and you don't like typing in 9.81. But you know it's a lot easier to type in than 9.81. I-10. It's not actually that much easier, but it's one character saved. So, let's say that you're making reference to that number right there. So your acceleration is negative this. Oh, not that. Just I-10. Now, unfortunately, if you were going to be copying this formula, there's a slight issue, because it's going to be trying to look here and here and here and all around the place, but your value is only in this box. So what you want to do is you want to add a $sign in front of both the I and the 10, saying that both your row and your column is fixed on this value right here. So let's say that this is your formula. So it's whatever this is times, 8. I don't know why that would be useful, but let's say it is. So now as you copy it, you're not going to get any errors, because it's always going to refer back to this one, no matter how far away you are going away from that value. Now, if you did not have this, and you tried to copy it, watch what happens. Oh, that's not good. You don't want that. So it's always important that if you're going to have a fixed value like this one, you need to put $signs in front of it, or else it's not going to copy the fixed position of this point of data. It's going to capture the relative position, and that's not going to be useful for you. I just wanted to show one more application of the Google Sheets formula function. So here we have the time and position data of an oscillating spring, and we're trying to calculate the potential spring energy at each point. Now there's 100 pieces of data here, and to do this by hand would frankly take a very long time. So we're going to use formulas. Always remember to set E equals, because otherwise you're going to be very sad. First thing we have is a constant 0.5, and the formula potential spring energy is equal to half of kx squared, where k is the spring constant, times the spring constant, which is here. Now remember, we're going to want to put $signs in front of both the letter and the number to let Sheets know that we are referencing a specific point in the spreadsheet, not a relative point, times the point right next to it, which is the position in meters, which is x squared. Now we're just going to drag this all the way down for all 100 data points. There we go. And now, using the tricks I taught you earlier, we can create a potential spring energy over time graph. I want to make sure that you are pasting everything. Sometimes it can be a little finicky about this. want to insert a chart. Now, as you can see, this time it did not work out the way we wanted to, so we're going to have to go in and fix it manually. So the first thing is we want this to be title, potential spring energy in joules versus time in seconds. Now then, first of all, we want to use row 5 as headers. So that way it knows that we have time and potential spring energy. And also we want to use column B as labels because that is our axis. And now everything is looking a lot better. So now we actually have the potential spring energy is oscillating just like we would expect on an oscillating spring. Our title is right. We just need to title our axes. Very important. So this is time in seconds. And our left vertical axis is spring energy in joules. There we go. Now, one small issue with Google Sheets is that whenever you try to set a trend line, it does not have an option for a sine, cosine, or really any kind of sinusoidal wave. It also doesn't have options for logarithmic patterns. There's definitely some room for improvement as far as graphing software. Which again, if you do have a situation like this, I might recommend a different program such as Logger Pro, or if you have a direct program such as Veneer's own lab data, sometimes you can export graphs directly from the data, and that will sometimes work a little bit better for you. With the only issue being that you're going to have to end up exporting it as something like a picture file rather than something that you can modify like this. Because the nice thing about these Google Sheets graphs is that if you ever mess something up, you can just go in and just fix it. And also you can change things like formatting, and it's a vector graphic, so it scales and all these different things that are nice. And if you use something like Logger Pro and have to export as a picture, things are not going to work as well for you. But you can also get a little bit more complex things, such as more trend lines that are a little bit better for you. So really it depends on your situation and what's required of you. Alright, thank you for watching this little tutorial on how to use Google Sheets in order to make your lab data work for you. Just one little addendum, if you ever have trouble inserting a sheet and having it recognize both an X and Y axis and trying to plot the two data against each other, my recommendation is to go in and try to set the significant figures of each equal to one another. So for example, if our time versus energy graph hadn't worked, the first thing I would have tried is to take our energy and make sure that it's only having the same amount of significant figures that this one does.